This is Edexcel Corpio 1. It's chapter 1, so it's the complex numbers chapter. It's not too big of a chapter, and I just thought I'd go through and then do some of what I think look to be the hardest questions in this chapter. Just, from a quick glance, I've not really looked into them too much. But I've just picked out a few questions and all of the challenge questions, and I'm just going to go through them and do them. So the first question is this. So expand this. Well, you could just write it out as a double bracket. And you've got a squared plus 2abi plus b squared I squared. I squared is defined to be minus 1, so that's just minus 1, and that's your answer. Hence or otherwise find this, and you want it in this form here. What this is hinting at is we want to use the idea this in this, right? So what I'm guessing is that we're going to be able to write this 40 minus 42i in this form here, so that the squares and square root cancels. Now, I have done a question like this in my grade 9 plus paper. So if you've seen that, then you'll definitely know how to do this. But yeah, so I wrote it like this, and I just said, okay, well, we'll probably be able to write this in the same form here. Okay, it's equivalent, by the way, so it's identical on both sides. Just square both sides, and then just expand this to get that. And then I put the real parts together and the imaginary parts together. So 40 equals a squared minus b squared, and minus 42 equals 2ab. Okay, I rearranged for one of them. I picked b, so b equals minus 21 over a, and I plugged that into there to get this. Just expand out a little bit, use a calculator maybe for that. You don't actually have to. You could just do a quick, column multiplication. It's not too difficult. Multiply by a squared on both sides, you'll get this. Rearrange to get this. I did a quick substitution, so a squared equals t. You'll get this. That factorizes into this. It's quite hard to see this, but you do have a calculator. You could just put it in if you really wanted to. You'll get a squared equals minus 9, a squared equals 49. I've just put a squared equals t back into there and then solved to get this. So a equals plus or minus 3i, or a equals plus or minus 7. Now, 3i, regardless of whether it's plus or minus, is not an integer, so you can just already discard that solution. And then a and b are positive integers, so you're probably going to want the positive 7. So we'll pick positive 7. Remember, b equals this. This should say a, not b. I don't know why that says b. That's a mistype. So imagine this says a. Okay, so you have b equals minus 21 over 7, which gives us b is minus 3. Now, even though a and b are both positive, it's fine if b is minus 3 here. I'll show you why in just a second. Okay, so I'm just going to plug in a equals 7, b equals 3 into there, and then the square roots cancel, and that's fine. That's because you've got a minus sign here, but b, if you just imagine b as being this positive 3, then this is still fine, because that just refers to this b here instead of this full thing, I'm guessing. But anyways, this is the right answer. We've got this quintic equation where b, c, d, e, f are real. Minus 2 is a solution, so is 2i, so is 1 plus I. Find the values of b, c, d, e, f. Now, for any polynomial, for any complex solution, the complex conjugate will also be a solution, or a root, shall I say. So other roots are complex conjugates, right? So if 1 plus I is a root, then 1 minus I is also a root. If 2i is a root, so is minus 2i. And obviously 2i is a root itself, and so is 1 plus I, and then minus 2 is also just a root. You don't say that 2 is also a root, because this is not a complex number, right? And then so I chose to write these as factors. Solutions are going to be z equals 1 minus I. Okay, so if you write it as a factor, it's z minus this. If you imagine an equals 0 sign here, and you bring that to this side, you'll get z equals 1 minus I, which is this. Do that for all of them, you'll get this. This I'm hoping you can see that if this is a factor, right, then the factor must equal 0. So if you make that equal to 0 and you bring the minus 2 to this side, you'll have z equals minus 2 as a root, because it is a root. Anyways, if these are all factors of this, there's 1, 2, 3, 4, 5, so this must be all factors, right? So we'll just multiply them together to get this. Just go really slowly with this. I mean, it's probably easiest to go with these two here, because the middle term will cancel, so you'll just have minus 4i squared, but I squared is just minus 1, so you'll have a plus 4, and then do that, so z squared plus 4 multiplied by this, and then multiply that by this and that, and then eventually you'll get this. Okay, careful, there's no z to the power of 4 like there is here, so b is 0, c is 2, d is 4, e is minus 8, and f is 16. Explain why a cubic equation with real coefficients cannot have a repeated non-real root. Now, a cubic looks something like this, right? And I wrote quite a long answer for this, but basically, if you have a non-real root, then there must be another root. So for every imaginary root, you'll have another root, which is just a complex conjugate. But the problem with that is you'll have an extra root because a polynomial of degree 3 has only 3 roots. Okay, so say you have an x cubed here, so there's only going to be 3 solutions. So you have 2 real and then 1 imaginary. But if you have 1 imaginary, we'll call it z, then z star, which will just be the complex conjugate, would also be a root. So then in fact you'd have 4 roots. Therefore it would be a quartic and not cubic. By means of an example, show that a quartic equation with real coefficients can have a repeated non-real root. Now, let's just randomly say that a minus I is a repeated root. Okay, this we're just making up our own quartic, right? That means that you've got this twice, okay, and then obviously because this is imaginary, you'll have imaginary solutions here. Their complex conjugates must also be solutions. So a plus I and then a plus I. To expand this out, the best way to do this is this multiplied by this, then this multiplied by this, because this multiplied by this will give you a squared plus, well, it'll be a squared plus, and then the middle term will cancel, and then you'll have a minus I squared, but I squared is minus 1, so it'll be a squared plus 1, and then a squared plus 1 multiplied by a squared plus 1, which is just a squared plus 1 all squared, and then just expand that to get a to the 4 plus 2a squared plus 1 equals 0, and that's my quartic equation. Now we're going through the some questions that I picked out, which I thought looked difficult. I kind of just picked the questions which had the highest marks, I can't lie. Anyways, f of 4 equals 0, we've got this. We don't have p, so we'll just plug in z equals 4. Expand this out, this is 256. 4 cubed is 64, 64 times by 2 is 128. 256 take away 128 is 128. 4 squared is 16, 16 times 5 is 80. 128 take away 80, 4p, and then this is just 24, obviously. Like I said, that's 128, and then yeah, just evaluate this. You get 72 plus 4p. This f of 4, this is f of 4 here, by the way. That equals 0, so set it equal to 0. Bring that to the other side, so p equals minus 18. Put p equals minus 18 into there, and that's fine. We want to solve it completely, so we know that 4 is one of the roots, therefore z minus 4 is a factor. And I can just say that the other factor is just some other cubic, okay? The intended solution is to use synthetic division. I'm not going to use that because it's kind of long and I don't want to use it. But yeah, so I'm just going to say that if we have one linear factor, the only way to get a z to the power of 4 is to multiply it by some other polynomial of degree 3. Okay, and that's just the general form for a polynomial of degree 3. Okay, just by inspection, the only way to get a 1z to the power of 4 is to do z multiplied by az cubed. So az to the power of 4 equals z to the power of 4. Now, because you're equating coefficients, which is z to the power of 4, this a just must be equal to 1. And the only way to get a plus 24 is to do minus 4 multiplied by d. Therefore, d must be minus 6, because minus 4 multiplied by minus 6 equals 24. So that's the case there. Now, let's have a look at z squares. Now, how do you get z square here? The way to get z squared is, well, one way is to do minus 4 multiplied by z squared, right, which would be minus 4bz squared. And then the other way is to do, z multiplied by cz, right? So that's going to be a positive cz squared. So minus 4bz squared plus cz squared is the only ways to get z squares from this. And we want, a minus 5z squared. Okay, that's just by equating coefficients because this and this are identical. Okay, cancel the z squares, you'll get this. I don't know why I put that in red, actually, I can't really remember. Oh, right, because I'm going to go solve it simultaneously later on. Okay, and then the only way to get z's, right, is to do is to do, what have I done first? Let's see. Okay, yeah, I've done minus 4 multiplied by cz. That's one way to get a z. And then the other way is to do z multiplied by minus 6. So minus 4cz minus 6z is the only way to get z's. The z's are minus 18z. Okay, and then cancel the z's, you'll get this. Just rearrange for c, you'll get c equals 3. C equals 3, put that into there, and then just rearrange for b, you'll get 2, and then plug that into there to have this. I just quickly checked in my head. I just thought to put, let me just check if z equals 1 is a solution of this thing in red. I put it in, it does actually give you 0. So z equals 1 is a solution. So you can say that it's z minus 1, which is the factor when z equals 1, multiplied by some quadratic will give us this here. And so this is identical to this, right? And this is identical to this. Okay, we'll do the exact same trick as we did last time. We want a 1z cubed. That means that a here has to be 1. C, the only way to get a minus 6 is to do minus 1 multiplied by c. So c just must be 6. Like this. And then just for checking z's here, what's the only way to get a z? Well, what I did was, we have 6z minus bz equals 3z in my head. And then I cancelled the z's, rearranged for b, you get b equals 3. So you have that. It factorizes into this completely. This doesn't factorize anymore. This has imaginary solutions. So this must be equal to 0, this is equal to 0, this is equal to 0. I'll put this into the quadratic form, you get this. Just simplify this here. You'll get minus 15, but that's just the same thing as square root 15i. So these are two solutions here, and then you've got another solution here and another solution here. Z equals 4, Z equals 1. So in total you have 4 solutions, and that makes sense because a polynomial of degree n has n solutions, as we've seen in that challenge question. Given that z equals x plus iy, this is just a general form, and z star is a complex conjugate, just use this to find out what x and y are. Okay, so z star, which is complex conjugate, is going to just be x minus iy. Hopefully you can see that. And then just plug in z star into here, plug in z into there. You'll get this. Expand out carefully. This is 4ix, and then minus 4i squared y. You'll have this. And then I squared is just minus 1. So this becomes a plus 4y. And then what I did was, the real parts must match up with the real parts on this side. And then the imaginary parts must match up with the imaginary parts on this side. So x plus 4y equals minus 3. And then y plus 4x equals 18. Rearrange for y here, so y equals 18 minus 4x, 18 minus 4x into there, you'll get this. Expand out carefully. The way that you can do this is, I just said that, 18 is the same thing as saying 9 times by 2. That's like saying 9 times by 2 times by 4. 9 times 2 times 4. If I do the 4 times 2 first, you'll have 8, and then I'll do 9 times by 8, which is 72, which is much easier than just doing 18 times 4, if you want. It's not too difficult, actually, looking at it now. Anyways, yeah, 4 times 4 is 16. It's a minus 4, anyways, minus 16. Anyways, you'll get this. So that means x equals 5. Plug this into there. So y plus 20 equals 18. So y equals minus 2. And that's that. Next question. We've got a complex number z. It's like this. And we want it in this form here. Whenever you have a complex, like whenever you have I on the denominator, it's just irrational. And we want to rationalize it because we want a and b to be rational in this form here. So we'll multiply by the complex conjugate, which is 4 minus qi, top and bottom. This here is 16 minus q squared I squared, but I squared is just minus 1, so it's 16 plus q squared. This here, this is, just expand this. I mean, you know how to expand this, I can't lie, I'm not going to go through it. You'll get that. What I did was I factorized out the I to get this, and then I split this fraction up down the middle, kind of like this. So I said that a equals this here and b equals this here, and that's fine. You can say that. It doesn't have to be like some integers because it just says it's rational. This is rational. This is rational. That's fine. That's the answer done. Thank you for watching.